Hi there. Thank you for clicking on this video. This video is the first of two videos on composition of functions, and I decided to break this up into two videos for a couple reasons. One, I think this is a weird and random enough topic that it deserves some treatment into like, what is it and why should we do it? Otherwise, you're gonna left wondering who would think of this and why do we make students do it? And the other is that things are absolutely crazy here. And I wanted to make sure that I was covering some content, but I don't have time to do all like the problem sets and work them out and all that. And so this made this weekend a little bit more straightforward. So please give this video a thumbs up if you find it helpful. Subscribe to the channel for more math content. Drop a comment or question to engage, and check out the many other videos and playlists on the channel. I'll be sure to link those at the end. I think it's the Desmos playlist. I'm going to go ahead and link at the end because there's a lot of other content that is out there. So I want to begin this by considering this situation. So you're shopping for a t-shirt. The cost on the price tag is $25. There's a sign saying the entire store is 20% off the displayed price. So we got some kind of clearance going on. I don't know what's going on, but 20% off the entire store. You also know that a 10% sales tax will be applied at the checkout. How much will you end up paying for the shirt? So like when it comes down to it, you got a certain amount of money in your pocket. Do you have enough money to pay for the shirt? So pause the video and take a few minutes to figure this out. Great. Let's look at the solution together. I'm actually going to talk through this a couple different ways because of the way I'm going to set up this problem in a little bit. So we have the price on the price tag is $25. The discount is 20% and the tax is 10%. So essentially we've got two problems here. And one way that you might think of this is the discount is $25 minus 20% of 25. Okay, that's essentially what we're doing because we're taking something off. And so you could think of it this way, 20% is 0.0 of typically means multiplication. And so we've got that. So 25 minus 0.2 of 25. And so we have 25 minus 0.2 of 25, which is, I did this out earlier. You'd think I would remember it, 5, right? And so it's 25 minus 5 or $20. Now, another way to do that is more efficient, but you might not think of it on your own. My inclination is to think of it this way, is like a discount is subtraction, therefore I should subtract something. But you could also think of it this way. If you're taking 20% off, then you're going to be paying 80%, okay? And so another way to get to that $20 is to say, I'm going to pay 80% of 25. And so that would be 0.8 of is times 25, and you can get the $20 that way. That is a more efficient way, and you can work from the first way over to the second way. If you think of it as it is 125 minus 0.225, which leaves you with 0.825. So 1 minus 0.2 would give you the 0.8. Okay, this is the way that we're going to look at it a little bit later. So I wanted to make sure I addressed that, because if you did it the first way and then suddenly I'm doing it this different way and you're like, wait a minute, where did that come from? So wanted to make sure I addressed that. Now, after you get the $20, so you're standing there in the store, you're like, awesome, 20% off. I'm going to pay $20, and you're going to take it to the cash register, and they are going to apply a 10% sales tax to that. So again, there's two ways you can reason this out. You could say it is $20 plus 10% of $20. Okay, so it's 20 plus 0.1 times 20, and 0.1 times 20 is 2. And so the final cost of the t-shirt will be $22. The other way you could think of it is this. You could say we want 110% of $20. Okay, because you want the 100% of the $20 plus 10% more. So it's going to be 110% of the $20, and that would convert to 1.1. And so you can get there that way. And as before, you can reason from one to the other. So this is 120 plus 0.1, and 1 plus 0.1 would give you 1.1. Okay, so multiple ways to reason that. And as I said on the last one, this is what we're going to be using as we move forward in the problem. So $22 is what you are going to pay when you get to the register. Now consider this. You have two friends with you. One of them wants a pair of jeans for $40. That's the price on the price tag. And the other is looking for a jacket, or looking at a jacket that costs $65. What will they pay? Okay, what are they going to pay? And so thinking about this, don't pause the video, all right? Doing two calculations every time is inefficient. You figure when we did that problem, we had to do two separate calculations. We had to find what is the 20% discount, and then what is 10% for the tax. And so you have to find one and then like physically do this other calculation. It works. And if you only were looking at the t-shirt, then it would be fine. But if you know you're going to do the same two calculations over and over, so you want to do it, but your friend wants to do it and they want to do it, and like you're all paying separately. I've used an example in my classes of like an oil spill where you're looking at the area covered by the oil spill. You're not looking at it at just one point in time. You actually want the area over like many points in time. So if that's the case, we want to find a better way to do this. We're better off finding a way to combine the two calculations together into one calculation, because that's just going to be more efficient for us. Now, that is essentially what composition is. Composition is the combining of two functions and like processes into one process to save time, to save computer memory. Like we do the composition. Okay, so we're going to dive a little bit deeper here and look at this specific example and kind of establish what the composition is. So the discount function, we're going to call that d of x, okay, d for discount, and x is the price of whatever we're buying. And we know it's a 20% discount, so the version of that we're going to use is the 0.8. Okay, so we're going to be paying 80%. That is our discount. The tax function, we'll call that t of x for tax. And we know that that is going to be 1.1 or 110% times whatever the price of the item is. All right, and so we've got these two separate functions. We got the function that tells us the discount and the function that tells us the tax. Now, these are two separate things, and we are going to combine them. So the question we want to ask ourselves is, what are we taking the tax on? Well, we are taking the tax on the discounted price. And that's where we get this order in here. Okay, so we're going to take the discount and then take that, the answer to that, and we're going to put that into the tax. Okay, which we know we did before because we took the 20 and then the 20 is the number that we carried over. So what that might look like here is this. We are going to take this d of x, and that is what we're going to carry over into this function over here. And what that means is in that first part, we would probably put the t of d of x, and then we're going to take this and make sure we plug it in for the x. All right, so what does this end up looking like? It looks like this. It looks like a t, but instead of plugging in an x, we are going to plug in the discounted price. So we're actually going to bring in the d of x. We're going to bring in that discounted price. That's what we're going to be plugging in. And so on the other side, instead of 1.1 times x, okay, which would just be a price, we're going to do 1.1 times the discounted price, which was 0.8x. Okay, and we can actually simplify that a little bit further. So we have T of D of X, and we would just do 1.1 times 0.8, which is 0.88x. So what that tells us is that instead of multiplying by 0.8 and then taking that number and multiplying by 1.1, we could just take the price on the price tag and multiply that by 0.88. And that would jump over that middle step and get us right to this is what I'm going to have to pay when I go to the register. So composition essentially is plugging one function into another one. The symbol that we use for it is this open circle, okay, open circle. And what I'm going to do is put the functions on either side. So we got that operator there. Now, if you watched my video on operations, and I'll go ahead and link that up there in the upper right-hand corner for you. You know, I made a big deal about when you're multiplying functions, you have to use a closed circle. Like you can't make it all bubbly because when you're doing composition, composition is represented by the open circle. What does that mean? Oh, in our problem, then what we had was T of D. What it means is take function f, and instead of taking like the function of a variable x, you're going to take the function of or f of this other output. So in our case, we had our tax function, and what we were plugging into the tax function was the discounted function there. How do we say this out loud? Well, we say it this way, f of, and instead of saying f of x, we would say f of g of x. So a little bit cumbersome. Now, in like everyday language, do we sometimes say fog? Yeah, sometimes we say fog. Don't say that officially. If somebody were to ask you, what are you studying in algebra? Like we're doing fog. They would absolutely know what you meant, but it is not official math verbiage. So don't say that like in a college interview or something. It is composition of functions, and the way that we say that is f of g of x. So let's revisit the earlier example that we had. We had the $40 pair of jeans. So what we established was this composite function called T of D of X, and that was 0.88. And so what we're going to do there is plug in 40. And so we have 0.88 times 40, which is 3520. Okay, and we can do the same thing over here. We can say T of D of 65 is simply 0.88 times 65, which is 5720. And so essentially the composition creates a new function that is more efficient. It can also show us how two functions might be related, which is an interesting question, which we'll explore when we do inverses. But if you've got like two functions that are related in a particular way, composition is one way of figuring out like, what that is. It can also show you that like maybe two functions are the equivalent of say adding 5. Like in this case, it was, multiplying by 0.88. So the main reason that we do composition is that it is more efficient when you have situations where you are going to repeatedly be carrying out the same two things. And I like introducing this concept this way, because if your teacher just says to you, well, like, f of x equals x squared and g of x is equal to x plus 2, and now we're going to do like f of g of x, and and doesn't really explain I really think it leaves a lot of students wondering who thought this up. Like, why would I want to plug something into another thing? So doing a quick lesson on this, short 15-minute lesson, just gives you some context of what composition is and why this is an interesting thing to do. And in the next video, we'll look at the ways that you can execute this process more efficiently. Please don't forget to like this video if you found this video helpful. Subscribe for more math help. Drop a comment or question below, and check out the many other videos and playlists on the channel. I've got a whole playlist on Desmos, so I'm going to link that here so that you can check that out. And I hope to see you in a future video.